we've just started recording, and just to recap what we were talking about. So we are building quite a large smart contract, and what I've done, and I'll go through in a minute, is done the individual parts with Blockly, but then we're going to have to use Haskell to generalize those into much bigger contracts. So we've got a Blockly for one round, and we want to build a contract for 10,000 rounds out of that. I was hoping to show some of that generalization today, but I have encountered some issues in the Haskell editor. Specifically, it's not a compile time bug, it's actually a runtime bug that happens. So right now, inside the tool, I won't be able to do that. So the next step for me would be to actually clone the Marlowe code from GitHub and try and run it locally on my own computer. And I guess investigate why it's crashing and see if I can possibly fix it. Anyway, having said that, I'm going to start with the constituent parts of the contract that you had sent me. So
thank you.
The first one is just a
I don't see your screen yet.
Oh, I'm sorry. I thought.
There we go.
Okay, you can see it now. Have you not been able to see it all this time? That's okay. I guess I wasn't showing anything. Sorry about that.
That's okay. We're good.
Okay. So what I'm going to do is just paste my first contract. So the first one we're talking about is just buying some WITM, or we think it matters. I'll just call it WITM.
Okay. I like it, WITM.
Yeah, for some dollars. So this is kind of how I would model that. And can we zoom in and out? Oh, yes, we can. Perfect.
And a little important typo is it's WTIM.
Oh, wow. We think it matters. Oh, man. Okay, yes, I've copied it all over the place. Okay. Yeah. I'm just in the interest of time. I'll fix it.
No worries.
It needs fixing for sure. That's not an easy thing to pronounce. Then I guess that's maybe why. Anyway.
Yeah.
Cool.
WTIM.
WTIM. Yeah, we think it matters tokens. Okay. So I'm not going to fix it now just because it's all over the place.
No, that's fine.
But we can fix it after the fact. So essentially, the first contract we're doing is reasonably simple. But it involves an observation of the outside world, because somebody's buying, we think it matters tokens with
an advertiser.
Yeah, an advertiser. And I think so an advertiser is buying these for dollars, and obviously dollars isn't something that's that lives on the blockchain. So what this essentially requires is for somebody to verify that they received number of dollars into their bank account or on their credit, through some mainstream payment method, and then confirm that to the smart contract. So that's essentially what I have. That's essentially what I have here. I've got we think it matters, making a choice, which is basically confirming the number of dollars that were deposited. And right now I've got between 0 and 100. Obviously that in reality is going to be much bigger in terms of the range of the dollars that can be deposited. We could just put 1,000, couples. Yeah, we'll add a couple of zeros. So now we're in 10,000. One more. Okay, so we can go up to 100,000, say. Right. So what they do is basically this choice is a confirmation that the money was received. And again, if no money was received, we close. Once we have confirmed that the money was received, then we think it matters will deposit some we think it matters tokens, which is this token here. And from then on, they'll deposit that into their own account. And then immediately they will pay the advertiser that same amount of tokens. So the main thing here is that the amount deposited should be exact, like the amount I've chosen the choice here, which means that I've chosen the value that was chosen in this choice here. So
Gotcha.
the amount deposited will be exactly the dollars deposited, because we said 1 for 1.
1 for 1. The same amount of dollars is the same amount of WTIM tokens.
Yeah. Although, now that I think about it, for later reasons, we might have to rethink that assumption. But let's just go with this for now. That was the original spec.
Yeah, that's the good deal everyone's getting right now if they advertise today.
Yeah, that's right. And I'll tell you why in reality it may have to be more, but just let's get to the second part before we do that. Cool. So yeah, and as soon as that money is deposited, as soon as those tokens are deposited, there's nothing to do. We just pay them to the advertiser.
Yep.
Okay.
So now they're in the advertiser's account.
Well, yeah,
they're in WTIM's account, but accredited to the advertiser.
Yeah, from the WTIM's account directly to the advertiser. So if this happens, then the advertiser has those WTIMs, which means they've bought them now and the contract is finished.
Gotcha.
So that's the first part. That's very simple, but that was kind of part 1. So any questions about this?
No,
cool.
No, just so people are clear, this is one part of a multi-part smart contract.
Yes, that's right. Yeah. So I've done the small parts, and like I said, it's going to need some generalization and then some gluing together with Haskell. But yeah, I'm showing the kind of separate parts. Although you can just see, all like from this point of view, all we need to do is basically plug in the next smart contract in here instead of closing.
Yeah, but this makes it nice to see each part of the contract instead of seeing it all as one huge jumble.
Oh yeah, and as it grows, it just becomes unmaintainable. So hence doing it like this. Okay.
Thank you.
So now part 2 is the more interesting part, which is going to be 1 round of voting. So I'm going to go back to simulation, reset here, paste that in. Yeah, so you can see that's quite big. Okay, so let's just go through it slowly. First of all, I've got the advertiser depositing 10 WTIM into...
And you got the token on the right, the WTIM's right this time.
Oh, I did too. Cool. Okay, so it's just that first one. Great. That's encouraging.
Yes, very.
Yeah. So just trust me why I chose 10, and I'll explain it as we move down the contract here.
Okay.
But really, if we were to stitch it together with the other contract, then we wouldn't have this deposit at all. We would just, that money would already be in the account, right, from the previous
contract.
From the previous contract. Cool. I just always start off with deposits because then this thing kind of can be tested in a self-contained way.
Oh, that's awesome. That makes sense. Yeah, I see what you're saying. When you're doing that simulation.
Yeah, that's right. So this kind of outer shell where you just, I guess, deposit everybody's parts, then you can just kind of do that. And then this part here is the actual part that you would slot into the other contract. And I guess you can think of this outside deposit as like a test harness, if you like.
I love it. Test harness.
Yeah,
that's awesome.
Yeah, like kind of. Because I have done some thinking about, obviously, when we make these production ready, it's going to take a little bit more testing than just running through the simulator.
For sure.
And I think when we write these in Haskell, it's going to be important to make them testable and kind of give them test scripts that execute against that use the simulator internally, but without the UI, and kind of go, yeah, this test script was successful, this one was not. So that's something that's not an immediate requirement, but it will be a requirement for sure.
Gotcha.
Anyway, cool. Right, and then we've got a vote happening, right? So the vote is being done by a member, and they're choosing between non-profit 1 and non-profit 2, right? So the choice bounds are between 1 and 2. So this is their vote, essentially. And then I've got like an if. So basically, if the choice is equal to 1, then we pay non-profit 1. We'll go into the whole payment thing, but then if you, in the else part, so in the other case, if it's 2, then we pay non-profit 2.
Yep.
The rest of the 2 branches are the same, just who is paid is different. So one thing I noticed in Marlowe is that you can actually, at least in here and basically in Marlowe, I don't know what the underlying rules of Cardano are, but inside Marlowe, you can actually only pay integer amounts of tokens. So you can only pay whole tokens. So in other words, that requirement that we pay half of a token to one account and 0.1 of a token to other accounts just wasn't realizable. So what I did was multiply everything by 10, and then, we basically that makes everything more divisible. So you can pay 5 to non-profit 1, and then 1,
which is 50% of that original amount.
Yeah. So I've kind of scaled everything by 10, but it's the percentages are the same.
Yes, I see it.
That does fundamentally change the value of your token, right? But inside Marlowe, because they only allow really the payment of whole tokens, I don't actually see any other way of doing it. This is, I guess, obviously, like in the Bitcoin world, you can pay fractions of a Bitcoin.
Well, and I feel like there's maybe it's just not in the playground, but I know in ADA, it's down to the I can't remember what decimal place honestly right now, but it's
okay.
To the Lovelace, which is way less than 1 ADA.
Cool. Is ADA Lovelace? Awesome.
Yeah,
that's fantastic. Okay, so I guess I'm just.
But I see what you're saying. Inside of here.
Yeah.
You see what you're doing with the deposit amount.
Yeah, I'm just wondering when we're referring to an ADA token here, I wonder if we're actually talking about 1 Lovelace rather than 1 ADA. It's a good question, and it's one that we need to ask, because I guess the documentation isn't completely clear.
I'll bring it up.
Yeah. So like when you're just saying, when you just build a pay 1 ADA to someone, or what, it's not really ADA, right? It's just it's a token with currency empty string and token named empty string. Is that 1 Lovelace or 1 ADA? Because if it's 1 ADA, then
it should be able to be fractionalized.
Yeah, which this language doesn't allow, which leads me to suspect that it's actually 1 Lovelace. So in the case of WTIM, again, it would be the smallest. It would be the smallest token possible rather than a big one. So just
gotcha.
That's where I'm at, I guess. We can obviously scale these by any number, but at the moment I've just put in a 10 here, so that I can split it into, 5, 1, 1, 3.
Yep.
Yeah. Cool. Yeah, and we would have to.
And the reason those are like that is because 5 represents 50% that's
Yes.
going to the nonprofit.
Yes.
1 represents 10% that's going in the
Yeah.
one lottery, and 1 represents 1 that's 10% that's going into another lottery.
Correct. Yeah. Yeah, exactly right. So if you wanted to, maybe another way of doing it, it would be to use 100 as the total, like as one unit, and then then the numbers would correspond to actual percentages. Like instead of paying 5 here, we'd pay 50.
Gotcha.
That's sort of an arbitrary choice, but it's an interesting question. So if you could find out like what these numbers represent in terms of ADA, then we'd know, because I suspect that they represent the smallest possible tradable unit.
I'll ask for sure.
Cool. Awesome. Okay. Anyway, so what we do is we pay the nonprofit one 5, and then we pay the members account number 1, and then we pay that same members account number 2 another 1. So those are the accounts for the 2 lotteries, because there's 2 lottery accounts. Yeah. Cool. And then we pay, here I've got it wrong again. WTIM. I'm going to start fixing it. Yeah, so then we pay the other 30% to WTIM. And that's, yeah, at that point, this round of voting is finished. So the money's been allocated, and
that would be for one single vote in the campaign.
That would be for one single vote, right?
Yep.
So I've got a close in here, right? But what we would have to do is generate a whole other one of these and insert it into here, right? For the next one. So if there's like
every vote in the campaign.
Yeah. Yeah. So this would be like a deep, deep tree of like 10,000 of these nested inside each other, which is why it's kind of become, because the problem here is you can't really loop, right? The language is simple, and the language is simple for the good reason that if you can't loop, the whole thing ends up being completely verifiable and fixed size, which is great from the ability to prove that the smart contract doesn't, go into infinite loops or anything like that. But at the same time, it makes it awkward to do things like this. So that's when you have to actually just generate a huge contract, and that would be the next step, which we're unfortunately not going to be able to do in this lesson, but that would be the next step. Basically generating these and nesting them 10,000 deep.
Gotcha.
Yeah. And we would have to repeat that nesting in the case of the nonprofit 2-1, because that's kind of the same continuation here and here. So yeah, like I said, the else part is again, same identical code, just that 50% goes to nonprofit 2 instead of nonprofit 1, because that was the one that was voted for.
Yep.
So
inside of the smart contract, for example, say for We Think It Matters campaign,
yeah.
If it was a 10,000 vote campaign,
yeah,
all of those votes that were available to be cast would be written in the one contract, and then people would individually come in and perform that portion of the contract.
Yes, correct. So I've got it as one contract for a round, but what we would do, I mean, I can kind of show you how one, so if we just, hang on, if I just duplicate this whole thing, okay, so I've just duplicated that whole contract.
A vote.
Yeah, the vote, right, which is actually, so what we would do is, instead of closing there, we would jam this, we would put this into it. And the only thing is we'd have to change the member role as well. We'd have to make this member to, because it's different members that are voting, right?
Yep, and that's
Yeah,
the thing is 10,000 different members
yeah,
would each have to cast. But it
yeah,
could be, there could be 100,000 members. It's just the
yeah,
first 10,000 members that come to the contract.
yeah. Understand. So what you would do is update all of these things to member 2. And again, you have to generate this, right? There's no way of doing this by hand, which is why the Haskell.
You would do that inside of Haskell.
Yeah, yeah.
Yeah.
But essentially, if we just change all of the member to member 2.
And then that would, but this would have to be added to each else, right? So each one
Yeah,
of the else's would need
yeah.
their.
Yeah, both. It would have to be added into both. Like at the moment, we are in the continue as here, and then we would have to duplicate that as well.
So inside of Haskell, if you were to write this, would you be able to write a smaller size
Yeah.
contract that produced this, next contract after each one, or do you literally have to build out the whole tree?
That's the whole idea. So what you would do, unfortunately, the Haskell playground is broken. But what we could probably try do at the end of the lesson, and I want to do it at the end of the lesson because I want to go through all this kind of structure, and then show you how you can build one of these arbitrarily large structures. I guess just to prove, to kind of demonstrate to you that we can do it. It's going to take a bit of care writing this exact one, just because there's a bit of complexity, and I'm having basically issues with. I'll show you the issue that I'm having, so you'll know. But at the moment, this tool breaks on large system. But yeah, like what's useful in Haskell is you wouldn't have to repeat yourself here. So you wouldn't have to, like I'm just duplicating and putting things in again, but you wouldn't have to do that. What have I done? Sorry, I keep duplicating them rather than deleting them. Let me just tidy things up. Okay. Yeah, so you understand basically, that this would just keep going deep, 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 and it becomes so big that you couldn't use it in this tool. So what I'm actually going to do is just remove it here and take it back to a single contract, just to keep things nice and simple looking.
Thank you for showing that, though. I do understand what you're saying.
I think the concept is important to understand. So as long as you kind of understand that, what we're doing is using this as a base and then generalizing. So the main thing that we'd have to do, right, is, you generate one of these, and, the role is like member 0. Then we generate the same thing with member 1, and except we kind of have to do it backwards, right? We have to do the member 1 first, and then once we've generated that, we can generate the member 0, and we can put the member 1 in here for the member 0. So we kind of have to go from the last member up to the first, just so we can build it up as one big structure.
Gotcha.
In Haskell, because it's lazy, that almost makes no difference which order you do it. It just figures it out. But that's kind of where we're going. Okay. So how is that kind of conceptually, in terms of how this contract would look?
I'm sorry, what was that?
You okay with this contract kind of conceptually?
Yeah. So I'm good with this. I'm ready to keep on moving. Yeah.
Cool. Okay. So the next one we have is the lottery. And again, I've done this as a separate, this is again something that would ultimately have to be generated with Haskell, because it's again one of those things where it's a lottery amongst 10,000 potential members. So I've just written a simple one, and then again, this is something that would have to generalize in code. Okay.
And this would be the this would be a contract that executed after all of the other voting contracts executed.
Yes, correct. What's going on here? I think they don't like this. Cool. Okay, so again, I start with deposit, but that's only because I need to test this independently. So, like again, this would basically be our test harness for the actual part, which is this.
Nice. I love the test harness.
Yeah, I mean, you kind of have to do it because I think these get big enough that you can't really test it as one big thing. So you test the individual parts.
Well, I think it also helps you really, find errors a lot quicker and easier. I think when you're testing one smaller thing than a whole bunch of things at once.
Yeah. I mean, that's kind of the fundamental principle of software, that you break things down, you decompose them into simple parts, then you implement those simple parts, and then you compose them up into a larger system. So the main thing is we have two members here, and they are both transferring. They're depositing into the lottery's account at this stage. So what we would have to do at the end of our previous smart contract, where every member had their own account set aside for the lottery, is there would have to be a step where we transfer from every member's lottery account into the shared lottery pool.
Okay.
I haven't done that part. I'm just kind of assuming that it's sort of done like this, but we would actually have to do it. So then the lottery draw happens, which is done by, I guess, a user called the lotteries, which is the trusted user who we trust to roll the dice. And at the moment, I've got it between 1 and 2, but this is, again, something that we would have to generalize. So it would actually have to be between 1 and n, where n is the number of, so if we've got 10,000 members that we're choosing a lottery from, then this choice would be between 1 and 10,000.
Yeah.
And there would be, 10,000 transfers of account balances into the whole lottery draw. Then, so what we have is, then it's quite simple. Then we just decide, we look at the lottery choice, and we check, well, if it was 1, then we pay member 1. And what I've done here, this is something we haven't seen. So instead of paying a fixed amount, what I'm saying here is pay the available currency from account 0 with the roll lottery, right? So basically meaning pay the full balance to member 1.
Gotcha.
From lottery, yeah. And then we've got the else part, which is, well, if it wasn't, if member 1 didn't win, then member 2 won. So same thing, except for we pay member 2.
And that would go on for as many as there were.
Yeah. So what we would do is, say there were 3, then we would insert another if here and duplicate that. So say there were 3, we can say, well, if it's equal to 2, then we pay member 2. Else we pay member 3.
And this is where in Haskell you have the ability to
generate this.
Yeah, just make it so it just does this itself.
Yeah, because obviously you can. It's not feasible to do this for 10,000 users.
Yeah,
and 10,000 is the minimum too. It has to, even if it was like any number of users between 1 and 10, in number, like quite a small number. Even then, you have the issue that like you don't necessarily know how many there are going to be. So while you can probably really painstakingly take your time and do one for a size 10, then you have to have a copy of it, which is size 9 and size, it's just a pain. So you have to generate these on the fly, which, yeah. So that's basically the lottery, right? So the key thing is that this lottery roll is trusted to roll the dice. I mean, that's going to be, we think it matters again, I presume, but basically a trusted party. So we have the 3 parts. So like I said, there's the aspect of generalizing all of them, and then there's the aspect of stitching it all together. So stitching it all together is kind of like, once we've generated the 3, we can just kind of stick one into the end of each thing. There's going to be a bit of duplication of them because like quite often, the next step is like, if we go to where was our if else? The next step of actually we should look at the other contract if I'm talking about next steps. But for example, in the lottery, in the voting part, regardless of whether the user chose, outcome 1 or not outcome 1, non-profit 1 or non-profit 2, the next step is the same, which is the next member comes along and makes a choice. So yeah, it's obviously these will end up very huge. And I would also, I haven't actually had a chance to try it, mainly because of the problem that I'm going to show you. But I imagine that we would get to a point here where this web application can't handle the size that we're talking about. I'd like to be pleasantly surprised, but experience. I would say that this is feasible for size 10, but not size 10,000. So what we're going to need is also the ability to simulate these things outside of this web tool, which is fine.
Gotcha.
But we'll need it. Okay. So the next thing I want to show you is, I guess, the error that I'm getting in the Haskell editor, which is quite frustrating. But so I'm going to take like the member vote round contract, which is like, and I'm just going to put it here. So basically we print, it was print.pretty contract, and then I'll say contract is equal to our whole contract that we had put in. So this is all fine. This is something that I briefly showed you in the last lesson.
Mm-hmm.
And when I hit compile, I get this concerning issue. Not a hexit call stack error called at ledger bytes. So this is inside Plutus ledger. So this is clearly a crash inside this tool's code.
Inside the testnet right now or something.
No, it's like inside this Marlowe playground. They are compiling Haskell and running it. And they are, if you look here in this Haskell program, this is just a kind of normal Haskell program, but it imports this language.marlowe library.
Uh-huh.
And this crash happens somewhere inside there, or more likely inside one of its dependencies. So I'm really unable to debug this in this tool. And it's definitely a crash. It's not a compile error, because if I make an obvious compile error, like instead of when, if I write when to, which doesn't exist, I get
an error,
a proper compile error. Yeah. So everything is compiling, but it crashes. It doesn't give an error message, but it just crashes.
Yeah, and this is new since the last time we went through this.
This is new since the last time. So I've done a little bit of I guess debugging of it. Mainly that, like, if I make it super simple and I just make the contract be equal to close, that's fine. but our contract fails for some reason. So the other thing I could do is make a super simple contract to say something like, I'll just continue with a close. So all it is when member one deposits, we do nothing. We'll send that to the simulator to get the code. Then we'll go to Haskell and we'll write that in. We'll compile again. And we get the same error. So it's strange, right? I
don't know. I'll ask them about that too.
Yeah, maybe like if they can fix it, that's great. But from my perspective, like what I would do next, and if I wanted to get this working, is to check out the Marlowe source code and basically play with it, try and reproduce this on my local machine, which is, you know, that's a reasonable thing to do. But of course, if you ask them about it and they just fix it, that's even better for me. Yeah. So I will send you like this simple case, like this simple program crashes basically. I'll email it to you so you have it. You can show them.
Cool.
So,
and hopefully they'll see it on this video too.
Yeah, well, yeah, sure. It still helps to paste it, you know, to give them a test case that they can use. So unfortunately, with something that simple, the code that I'm going to show you about how you could write something more general, is we're not going to be able to run it and actually show you because of this current problem. But I can still show you kind of what the code looks like. Okay.
Yeah, that's fine. We can always try running another time too.
Yeah, that's right. So what I'm going to do is, what we're basically going to do is make a real simple thing of, we'll take this, and what I want to do is just, well, essentially this, right? So what I'm going to, just to show you this idea of generalization with Haskell, is at the moment I've got, when member one deposits, then we close the contract. So what I want to do is kind of stack that, so we can do it to arbitrary number of members depositing. So member one, member zero, you know, member zero, member one, member two, member three. So I want to be able to generate this contract, but for any number of members. So basically what I'm saying is, you know, for two members, it would look like this.
Yep.
I guess we'll start at zero because in programming, counting starts at 0, and so on. So for any size. So that's the goal of what I kind of want to show you, how I would write that in Haskell. And because of the problems, I haven't written it yet. So we're going to kind of do some live coding.
That's cool.
So I'll just send this to simulator and I'll start with this. So, okay, let's go into Haskell. So what we're going to do is we're going to write a function, generate contract, gen contract, and it'll take an int, which is the number of sorry, where am I going with this? That's the number of
the
members that we want to do, and it'll return us a contract. Contract. Okay. So what we're basically going to do is, again, gen contract. Well, this is really common in Haskell. Like, so you do, we're just going to say, if there's 0 members, okay, then we just close. So that's what that looks like. So when this function takes the number 0, then we just close. So that's the, what we're going to do. This is, there's something called recursion, which is the idea of writing a function in terms of itself. We haven't covered this in the first Haskell lesson, but I guess we're going to quickly cover it now. It's a little bit of a trial by fire, but don't worry too much about it, understanding it completely. As long as you kind of get the concept, I'm happy. Like, you don't have to be able to rewrite this. Okay, so the 0 case is easy. Now, what we want to do is gen contract n. So the 0 case is the base case, and then we take it, then we do the case for an arbitrary n. And what we're going to do is something like this. So basically, we do a case, and what we're going to do here is instead of member1, we're going to have member plus show n. Show is a function that converts things to a string, basically.
Okay.
So at the moment it's an integer, and we're converting it to a string. So all it's going is from the number 1 to the string 1, and this plus plus thing concatenates strings together. So I'm just going to put this in brackets just to make sure that the precedence of things is okay. So that's like, for example, if we pass this with 2, then this is going to be member 2.
Gotcha.
Right? But the interesting part, all of the rest of it's the same, but the interesting part really happens here. So instead of closing, what we do is we do the same calculation, but for n 1 less, right? So what we're going to do is get contract n minus 1, right? So this is super weird.
Why is it minus 1?
Yeah. So I'll explain. I'll show you an example, I guess, because I think that's the. So basically, I see why you're asking minus 1. So what we do is our base case, we're going to get down to 0. So when there's 0 members, we just close, okay? When there's 1 member, then this is 1, and it's going to create us a member 1, and then it's going to do this recursive step, which is then going to be 0, so it's closed. So what it does is it kind of processes the current member, and then builds the contract for the 1 less, and then kind of builds it all together. Now, there's one issue here that, as I've put it, so this should compile, but it won't run. Okay. That's just complaining about this contract here, not because now we've got gen contract. So instead of calling contract, I'm just going to call like gen contract 2. Okay. Oh. I was afraid it would be too simple.
Just looking at this and trying to think in my mind what the different errors could be. That other error you got brought up was about the ledger, and I wonder if this playground isn't set up to let people use like put their own token.
Okay.
You know what I mean? Like, what if it's limited to you can only test this playground with ADA?
ADA. Okay. We can totally just verify that. So we can. I'm just gonna like put this.
Because I'm just thinking, that other error you're getting, it might just be because it's saying the ledger can't find WTIM token or something.
Sure. Yeah, that makes a lot of sense. Cool. I mean, that's not the error message, but I actually believe that that's a good hypothesis. So I'll just say contract. And I'll take one of them. And I'm just going to delete everywhere where it says WTIM. Yeah. Yeah, that did it. That fixed the issue.
Well, that's cool to know.
So
that's something to.
Well, let's think about it though. So I'm just going to go into the token.
It's kind of weird in the playground though. You can't play around with other.
Yeah. No. I think what this. It's the Haskell library seems to fail on it. The actual playground is fine, right? Because we've done this and tested it on. Oh, we didn't actually go. Actually, let me. Sorry, I just realized one thing we didn't do is actually do this lottery or this thing, because it does work in simulation. It's just that the Haskell code doesn't generate the code for the simulator. But yeah, that's great thought, you know. Cool. Well,
either way, let's continue with what you were doing. That just popped, you know. That,
yeah, no, awesome. I think we fixed it, but I think it's definitely like it's a bug that we found, and now we know which case it's into. So it doesn't seem to like WTIM. Because my understanding of how these tokens work is, according to the documentation, so there's a currency symbol and a token name. So a fungible token is represented by currency symbol for which there's exactly one token symbol. And a class of non-fungible tokens is a currency symbol with several token names. So in our case, because we want our tokens to be fungible, it should be this, you know, the currency symbol is WTIM, and there's only one token name, and I've just left that as empty string, just like ADA has an empty string there. So I believe that's the correct way of representing it, but
oh, and I'm sure it probably is. I'm just thinking that maybe the way that this, you know, the playground works is it just doesn't recognize anything but ADA right now.
Yeah. Okay. So despite that, let's try and write this this recursive. So this is what we had, and what this is complaining about is that you can't concatenate. This is something called a byte string, and this is a string. So those two things don't work together. And this is where I have to kind of go to the Haskell documentation and have a look at what to do. So there's a site called Hoogle. It's funny, and it's a little bit facetious with its name, but it's actually one of the most amazing developer tools that only exists for Haskell. So the idea is that you can search for functions only by their type. So we can write like bytes. So what we want to really do is we want to go byte string to byte string. So, and byte string. So I want to look for a function that appends two byte strings together. The way I know that these strings here are byte strings is basically only based on the error message. Okay, so it's called append, which makes sense.
It's a cool resource though, Hoogle.
Oh yeah, like it's amazing. So what I'm going to try do is import that, append. And then instead of member plus plus, I'm going to go append member show end. And that's still not good enough because now we were using the right function for byte strings, but show end is still a string, not a byte string. So we also need another function, string to byte string, like that. And yeah, it's called pack, and it's in this package, right? So I'll just import that as well.
And where are you importing these from?
So I am kind of assuming that they are already going to be there. So yeah, so these imports are basically just saying we have some libraries already set up in our environment when we're building this code.
Gotcha.
So this import means make these libraries available in this particular file.
Gotcha.
I'll just so we want to show and then pack, and that should now work. Now this could come back and bite me because it may well not actually work, but depending on, like, this is kind of one awkward thing about this Marlowe playground, that you don't know exactly what's available and what's not. And I guess this is what happened. Could not match expected type token name with.
Try putting ADA in there, ADA in there. See what happens when you run it with the ADA.
Oh no! This is not the. I'll show you. Okay, I'm just gonna make this simpler, and for now, I'm gonna note that I'm just gonna write member, right? So I'm not gonna try append anything to it. And then we'll make it ADA. Cool. So that works. So we're not done yet, right? But now you see I have
stagnant member.
I have a member and then another member, right? So we can, and if we do it with like 5, then we've got, you know, more depth, member. And if we send this to Blockly, you see now we've got a depth 5 set of cascade of deposits from the member.
They're not. It's the same member.
It's the same member, right? So now that's the issue that we're looking at, which let me try and debug. So the issue now is that I'm gonna try and append this n to the member, and that's definitely not going to compile, but I want to see the error. So could not match expected type token name with actual type char. Okay, so now what we have to do, this is where we hit the limits of kind of this tool, because we end up having to go to the Marlowe playground, to Marlowe, and looking at the definitions of things to kind of figure out how to. I wonder if we can look it up here. I doubt it. I don't know. See, because this is not a published package, you tend to not be able to look it up on this tool.
Gotcha.
We're stuck with code. And okay, so we've got this. And let me just see if I can find it. Language, Marlowe, and what was our error? Ledger value token name. Okay. Yeah. So I'll briefly, I think this might be a rabbit hole, and I'll certainly have it fixed by the next time. But I'll briefly explain to you what the error I'm dealing with, just so you're not just staring at me stare at the screen. So essentially, what I'm trying to do is find out a way to append the number to the member name, right? And that's not working. And the reason it's not working is because this string here is not actually a real string. Instead, it uses a Haskell type called, where's my error message? Ledger value token name, right? Which is a different type from a string. So you can't just kind of append things to it like you would with normal string manipulation in Haskell. So, I mean, yeah, which kind of puts us in an awkward spot because in order to figure out how to append this thing, I have to find the definition of this token name, which doesn't actually appear to be inside Marlowe. So I think it's going to be inside inside one of its dependencies. Which I'll just briefly. Okay, what other modules? Language Marlowe. But what does it depend on? Maybe. I'm just going to do a GitHub search for this type. No, that's not. Okay. So yeah, it's a strange little issue, and it's really one of the limitations of the tool that you can't get much more information about these types and look into them and figure out how to manipulate them. So I'll have to come back to you about
no worries.
how we would extend that. The concept is very simple, right? The concept is just we want to append a number to a string, but because this isn't a real string, it's a special token name type. It also concerns me because I think like a role isn't really a token name, but that's probably okay. They're both strings under the hood. So yeah, that's where we're at. So we've looked at the parts. I've perhaps unconvincingly showed you how you could make things bigger with Haskell for kind of arbitrary size. And yeah, I'd have to look into this bug. And I think at this stage, I'm gonna have to get this code loaded up locally and actually be able to look at it and compile things locally. Because I think for something like this, I think we're hitting the limits of this playground editor. So I'm sorry about that.
Oh, no worries.
But yeah, the next.
I get the concept of what you were.
Yeah, so it's just going to take a little fiddling, and kind of that's a lot of software development is just fiddling around and trying to make different types from different libraries play together the way you want. So that's one of those things that probably doesn't need to be done on screen anyway. But that would be the next step in extending this. Yeah, so in order to, so I've showed you the parts. In order to develop the real thing, I think, like I said before, we'd have to get Marlowe running and compiling locally, and hopefully even being able to run this simulator locally on my own computer rather than through this web tool, which is totally fine, but that's, yeah, it is a limitation of the web tool. And then we'd have to generalize the votes function to let you handle an arbitrary number of voters. extend the lottery to have an arbitrary number of participants, and then basically combine those three things into a big giant smart contract using Haskell, and then potentially we'd have to write some test cases and have a way of executing them. And the final thing that I didn't go through, but it's really just the opposite of the deposit process, is the actually cashing out at the end of it back into dollars.
Well, that gives us something to do again.
Yeah. So I think
pushing our time now.
Yeah. So before we carry on this, I'm going to look into cloning this code from GitHub and actually getting it running locally and seeing if I can do these examples on my own computer. Then at least we'll be able to write these more complex functions and have, I guess, have our usual tools to have my usual tools that I use when I'm doing Haskell development to figure out what types go with what. Mainly, I need to look at definitions, and this is kind of where I'm hitting a wall, just using this editor.
No worries. Yeah. I appreciate it. Again, it helped me learn a lot, and every time we go through one of these, it helps me put the pieces together a little bit better.
Sure. Cool. So we ran into a couple of issues, but I'm hoping the concept still came across.
Absolutely.
Cool. So I will stop recording.